En meters. Hallå, hallå. Ja, där är vi. Ser det bra ut? Ser det bra ut? Se till att nivåerna står i mitten. Ja, etta, tvåa, etta, tvåa. One, two. Etta, tvåa, etta, tvåa.
Hallå? Yes. Den här ska vara igång nu. Och den har också fullt batteri. Så det borde fungera. Testa. Bäbe vita lamm. 1, 2, 3. 1, 2, 3.
Sätt micken liksom lite på sidan av munnen. Eller sätt på den ordentligt.
Ja. Ja, det sätter vi på sån här då. Vi testar. Testa micken. Låter det här bra? Blir det här bra? 1, 2, 3. Hallå? Ja, det var ett tag sedan. De kan vara i rummet här bredvid. Jag vet inte om han var där. Man kanske kan sänka den här på något sätt. Nej, det verkar inte riktigt gå. Ja, channel 1 står det. Channel 1 574 700 MHz. Jaha, okej. Ja, det här är kanske kopplat till någon annan kanal i och för sig. Ja, blir någon sekund delay där. Ja, visst. Jag babblar. Jag snackar skit. Okej. Yes. 1, 2, 3 testing. 1, 2, 3 testing. Ja, jo. Ja, jo. Jag vet inte fan hur man sätter upp det här bäst. Talarna kommer säkert ha micken på väldigt mycket olika sätt också. Det får man testa på flera sätt. Yes. We're testing the microphone now, but it will be. Oh.
Hello? Ah. Good. Hear me? Ah, there we go. Okay. So I want to talk to you about how we boot from soft RAID volumes. And to start it off, I'd like to give you a short introduction on what soft RAID actually is and how it's used. So soft RAID emulates a SCSI bus, which means that you can essentially attach any number of virtual disks to it, and they will all appear as a separate SD device to the operating system. The disks themselves, the virtual disks, are usually known as disciplines, which are ways of sort of manipulating the I/O that's happening virtually inside the soft RAID subsystem. And each discipline can do anything that fits the SCSI model. So if you can express your I/O transformation in SCSI, you can write a soft RAID discipline for it. The currently available disciplines are RAID 015, and we have a crypto discipline for disk encryption, and we have a concat discipline which concatenates disks, so you can have more space. And when soft RAID was added, we already had some hardware RAID support which was called the BIO layer. And there was an existing utility to configure this and to make virtual RAID appear the same way to users. These subsystems share the same control utility. So soft RAID is configured with BIO CTL. So the underlying storage that soft RAID is using is modeled as, it just uses disk slices essentially from the disk label. So any partition you can put anywhere on any disk can be part of a soft RAID volume. And each chunk has a bit of metadata at the start to describe which soft RAID volume it's part of and what RAID type it is, what the size is, etc. So here you see the configuration where the disk SD9 is backed by two partitions. The first one is SD2D and the other one is SD3D. So this is actually the RAID 1 setup that I have in my desktop at home. That the whole system is on this RAID partition. So when you configure these volumes, they need to be sort of assembled. So you have UID that says which chunk belongs to a volume. So the common misconception is that you need to sort of make sure that your device names don't change if you have devices which are part of soft RAID, but that's not a problem because the kernel will automatically reassign device names if the disks are changed. And it can still go and find the correct chunks to put into the soft RAID volume. And so the metadata has this global volume UUID, which identifies which chunks belong to which volume, but it also has volume IDs, which ensures that if you have several soft RAID disks and you keep rebooting your system, they show up as the same disk every time, and they don't switch. And also the chunks have a similar way of maintaining order so that, for example, a concat disk can be attached in the correct order or can be built in the correct order. So again, a list of the disciplines. The RAID stuff should be obvious. The crypto stuff encrypts data, and it has two ways of unlocking the volume. So you have the passphrase and the key disk. And the key disk we're going to talk about in a bit. It's quite interesting. And you have concat. So one thing to know is that the current implementation does not support nesting. We have lots of people coming to the lists actually and saying, oh, I'm running RAID 1 on my NAS with OpenBSD, and then I put crypto on top to make sure my files are secure. And some people actually get this working. However, it's not officially supported yet, and you might have troubles with rebuilds and stuff like that if you do this kind of thing. So setting up a RAID 1 discipline is pretty easy. You don't have to take care about assembling it manually because the kernel will always auto-assemble it. You can boot from it on i386, AMD64, and SPARC64. And to install it, in the installer, you essentially break out from the installer prompt to a shell. Then you set up your disks, as shown here. You run fdisk on this is an RAID 1 setup with 2 disks, so you run fdisk on both disks. And then there's a compressed form which is based on the man page. It basically puts answers to the questions that disk label is asking when you run it interactively. And I use this because it fits on the slide. But you'll see other examples later where it looks more natural, like you would actually see it in the installer. So this basically configures 2 D slices on one on each disk. And then it runs BLCTL with a -C1 argument, which says, I want a RAID 1 setup. And you give it the slices that you want to use, and your disk appears. And now when you exit this shell, you will get the first prompt back, so you will again have the option to install, upgrade, etc. And then you just do install, and you select the software disk you created as the root disk. And everything will, from then on, behave just as if you had installed to the hard disk directly, except everything is on RAID 1. So a big improvement over earlier ways of doing RAID 1 on a full system setup is that you do not need a separate boot partition or anything like that anymore. This used to be the case, but nowadays it's been all magically arranged for you to do this work. The only thing we don't have yet is scripted support in the installer for setting up soft RAID. And that is something that people often send patches for in one form or another, like little hacks here and there to make it easier. However, there's supposed to be some utility that Joel Singh is writing, or has been writing for a long time, that's supposed to make all the setup stuff easier. Because I also once started a diff to make the install script handle soft RAID better. However, it got really hairy very quickly because if you don't want to support just very simple setups, but sort of like give people a real configuration mechanism for their RAID setup, then the shell script in the installer is just too limited. So the idea is actually to add another utility for this, which might be called srctl or something like that, which can then be run in the installer and do all the hard interactive configuration for you. But that doesn't exist yet. So right now, you just go to the shell at the start of each install and set up soft RAID with BLCTL. So the crypto discipline is very interesting, for example, for laptops. It encrypts data using AES ECB256. In the metadata, this is not fixed, so we could change it. However, the current binaries that we ship, they will all not accept anything but this. But there are ways to upgrade to other crypto algorithms should we need to. The idea is that you don't have to care about the algorithm. So we're not giving you hundreds of options about choosing crypto parameters. This is something that we're taking care of for you. We decided that this is correct, and we're going to use it. I think there are some gotchas with it, like if you have a disk full of zeros and you use this algorithm, then the disk zero sectors appear as zeros, so you can see which part of the disk are encrypted or not. If you care about that, if you don't want people to tell which blocks are encrypted and which aren't, you write random data to the whole disk before you start the install. And then the whole disk will appear random, and if you use encryption on top of this, nobody will be able to tell which blocks have been used and which have not been used yet. We support AES-NI thanks to Mike B in the new Intel CPUs and AMD CPUs. So, for example, on my X220 ThinkPad, I don't notice any slowdown whatsoever from using encryption. I do. On this one, I do. This one has an SSD in it, but it's slow, and the crypto makes it slower. Yeah, I mean, it's okay. You want crypto, so you pay the price. But if you have some particular hardware that supports AES-NI, then you really have no reason not to care, not to do it. So we can do full disk encryption setups on i386, AMD64, and SPARC64. where only the bootloader is not encrypted. Everything else is encrypted. And again, you have the options of using a passphrase that you type when you boot the system, or when you attach your soft-rate crypted disk manually while the system is running. Or you can use a key disk. So the installation this time for crypto shown a bit differently. Again, you break out to the shell at the start, you initialize the disk, and then you just add a departition of type RAID. That's very important. It needs to be RAID type. After that, you run the OCTL with just this one slice as an argument and give it the capital C option, which means crypto. And this time it asks you for a passphrase. You type it twice the same way, and you get your disk. And again, you exit the shell and continue the install on it. So the key disks can be put on any device because they're also just disk label slices, right? I mean, if you think of a key disk, you might think of a physical object, but actually it's a slice in the disk label. And that gives you quite some flexibility. If your key disk is, can be seen by the BIOS, so if you are at the boot prompt and you run machine disk info and you see the disk in the listing, then you can use it to unlock your system for boot, which means that if you don't have this disk inserted in your system, OpenBSD will not boot. It will just print a passphrase prompt and not do anything, because you cannot type the passphrase that comes from the key disk, because the key disk has some random data which protects your AES key. And for backup purposes, it's important to know that you have to skip the first 8K of the partition because of disk label and stuff like that. So have you ever DD'd into an A partition and removed your entire disk configuration? This is why. So these are the commands you can use to back up and restore your disk for reference. And they're pretty small, so you don't really need a lot of data. I had a hard time finding a USB key using less than 4 gigabytes for testing, and I didn't bother testing less than 1 megabyte on them because I had enough space. But yeah, you could in theory use a very, very tiny device. Also, since they're disk label slices, you can configure multiple ones on the same key disk. So for example, in my X220, I have an mSATA SSD and a spinning disk. And the system runs from the mSATA, and the home directory is on the spinning disk. So the key disk for that system looks like this. It will unlock the root file system using one of these disk label slices while it's booting, and by then the other key disk hasn't been used yet. The other key disk will be used when the kernel boots and actually auto-assembles all the crypto volumes it can see, and then it will auto-assemble the root one and the home, and then they just get mounted. So it's entirely transparent again, but I have a single USB device that I plug into the laptop and unplug. So with the key disk you install, but it's sort of like a mix of the RAID 1 and crypto setups. You have 2 disks. Again, you set a whole range RAID partition on a whole range OpenBSD on either of them, but you can, for the key disk, you could change that. It's not restricted really. You just need a small OpenBSD part and the key disk in it. But this just shows you how to do it. And then you pass the key disk with the -K flag, which is here. And again, it appears, you can install on it. Okay, so now I'd like to explain how this magic works. And I have to admit that over the last few days I've tried to figure out a bit more about how the i386 boot process actually works and how the Spark 64 boot process actually works from the beginning. And even though I've implemented the Spark 64 part, most of it, and I've implemented the key disk support in the boot part, I have no idea really how this stuff works in detail, so please don't ask me. It's just magic. So I understand everything up from the point when BIOS boot is running. Okay, before that it's MDR and super blocks and whatever. So what we had to do is that we had to modify install boot, and Joel Singh actually wrote a new install boot for other reasons, I think, that unifies the separate installable implementations we had, which were essentially per architecture. And this new installable has soft rate support built in, and it has hooks for each architecture, which put the bootloader stuff in the right place. And usually the right place is soft rate metadata, and then for the first level boot, you have some system-specific location. So on i386, we actually port the first stage bootloader, like our first stage bootloader, which is OpenBSD specific, into the software metadata area, and the MBR will load it from there. The MBR essentially looks at the partition table, the MS-DOS style partition table, and is pointed by some metadata in there. It's pointed at this location. It doesn't really know that there's software metadata there, of course, but it just jumps to that sector and executes the program that's written there. Spark 6.4 has open firmware, which is actually smart enough to read FFS file systems and disk labels. And so there's something called a super block, which I think is before the disk label, and that's where the installable program will put the first stage bootloader all the time. The second stage bootloader has to have some more smarts. It assembles soft rate volumes. It actually does the same thing that the kernel does when it looks for disks, for soft rate disks. It's a minimal implementation. Some of the checksum stuff is missing, for example. But it's really just needed to load one file of it, so it's not really that critical. It needs to find the right volume to load the kernel from, and it needs to tell the kernel that it was booted from soft rate, because otherwise you have the problem that the kernel boots up, and because it started, the bootloader starts the kernel and then the kernel takes over, and there's no way for the kernel to know which disk it was booted from while it's starting. And this information is usually passed on by the BIOS from the bootloader to the kernel somehow. And if you don't have soft rate support, then your kernel will just ask for the root file system and say, I cannot find init, which was what happened when we tried this the first time, and I tried this the first time. I ran into situations where I could boot the kernel, but it wouldn't find the root disk at all, and I had to always type boot-a, and it would ask me for the root file system, or I could actually change my kernel config and put the device name in there, but then every time I had to upgrade from snapshots, it broke, and so on. It was horrible. The OpenBSD kernel itself, again, when it runs, has to assemble volumes and actually really detect the root file system, as I just explained. So the section that installboot modifies looks like this. I think the skip part is MBR, disk label magic stuff. Not quite sure, but anyway, that part is always skipped. I think it's already inside the partition here, so we're already inside the chunk, right? We're inside this part that you gave to BOCTL, the partition. The metadata is essentially fixed size in terms of how large it is in total. However, there are optional items in there, so not all of it is always used. The bootloader part is coming after that, and it contains a single inode FFS file system containing boot. Now, why is there this single file system in there? It's because the installboot program knows how to figure out where BIOS boot is in terms of disk blocks when it reads FFS, because it has logic to map FFS structures to underlying disk blocks. And to avoid having to rewrite this logic, Joe Singh placed a little FFS file system inside this small section of the disk with just one inode. And this way we can reuse all the existing code that depends on this kind of capability. On Spark 6.4, it's just a plain copy of the OFW boot program that lives in there. Now the boot blocks is interesting because that actually contains the first stage on i386. So the boot blocks part is where the MBR loads the first stage from. On Spark 6.4 it's unused because on Spark 6.4 when we're booting we already have capabilities like disk labels in FFS from the firmware. We also have particular metadata. So the metadata has optional items which which can be added to express capabilities of software chunks that are not there for every chunk. And in this case, we actually save some disk label UIDs and stuff in there, which is interesting for later. So just keep this in mind. This has essentially the boot block size and loader size and some disk label UIDs in it. So the second stage bootloader on i386 will assemble the software volumes. It gets loaded by BIOS boot, which got loaded from the NVR. And now the software logic in the second stage kicks in, and it actually goes and reads the disk labels and reads the software metadata inside the partitions it's seeing, and matches up the UIDs and finds, basically internally has data structures that describe the software configuration. And then if you told it to boot from software, from a RAID 1, for example, it will just iterate through this list of chunks and find the first online one, which just means that it's not broken, as in you're not doing a rebuild on it, or the disk is not missing or something. And it loads the kernel binary from there straight, because it knows that there is an FFS file system in there, because every block on the RAID 1 is copied from to all the disks, right? So there's actually no special logic there. It's just a matter of identifying the right partition to read the kernel from. For crypto, there's additional complications, because you need to have I/O that decrypts and encrypts, and you need to deal with the passphrase and key disk situations. So the bootloader uses a very simple I/O system that has what's generally known as a strategy function, which also exists in the BSD kernel in general. It describes how to actually do I/O to a device. And we have strategy functions for the underlying physical disks. And when soft RAID is involved, this will actually redirect to soft RAID first, and then soft RAID will do the actual I/O. So there's a little strategy function specifically for soft RAID that, for example, does the encryption and decryption when it gets blocks from the physical disk. Another very important part is that the kernel needs to be told that it was booted from soft RAID, so we're also passing the UID of the software volume we're booting from, and for crypto we pass the mask key, because you do not want to type your passphrase twice, right? So the kernel will transparently assemble the crypto volume it's booted off. You have to type it twice, really, but that's because you're not typing well enough, good enough. Maybe we should put some insults in there, like in sudo, so you... Actually, backspace doesn't work in the boot prompt yet, in the passphrase prompt. Uwe has a diff to fix that, and it has been slacking in inboxes of me and Joe. But yeah, that actually would help me too. No. Oh, which questions? Sorry. So Henning was just complaining that he always has to type his password multiple times, regardless of how good the implementation tries to prevent that.
There is no technical solution.
And Ted is asking if he can have a backspace in his password, and I'm saying no. So the argument passing on i386 is quite hairy, and when I looked at this the first time to figure out how to do this for Spark, the approach seemed quite natural given the i386 situation, but then later it turns out that Spark needs something entirely different. So this is supposed to be a sort of architecture-independent way of passing boot arguments. However, it's used in a couple of architectures, but not all of them, because it relies on shared memory between the bootloader and the kernel. So there's a list, like a linked list of boot arguments, each of which is a struct that has a specific type and size. And below there you see the soft RAID argument type, which contains the UID and the mask key. The bootloader essentially fills this list in and writes it. So it's located at a location in memory that both the bootloader and kernel know about in advance. So there's no communication about where this list is. It's just a fixed value, and when the kernel boots, it reads it from there. And as you can see, this is something that allows you to be very flexible. That allows passing binary data to the kernel from the bootloader. It allows parsing things in arbitrary order, and so on. So when the kernel boots, we essentially lost all information except the arguments we passed in. And so it has to go again and assemble all the volumes. However, it has some hints from the bootloader that tell it, for example, what the UID is that it was booted of the volume that it was booted from, and what the mask key is in case it finds a crypto partition. And yeah, Henning has to enter the passphrase first, but no one else does. And because this the mask key is passed so early, if you only unlock one disk, you can just basically plug the USB key in, hit enter at the boot prompt, and plug it out again once the kernel. Because as soon as you see the kernel loading, it's already there. It's already been read, and it's going to be propagated in memory up to the point where the root file system is mounted. So now let's look at the Spark 6.4 situation. That was a bit different, and I had to learn quite a new set of things. For example, that you can have programming languages that get everything backwards. That was very, very interesting. If you ever want to learn a weird language, then I recommend this one. It's actually very good to learn because if you have a Spark system, then you actually can type code like this into the OK prompt. I thought it was like a dumb command-based system, but it's actually Turing complete. So Joel wrote this, had written the first level patches already quite a while before I started implementing from the top down. So I went and implemented the second bootloader parts, and based on what i386 was doing. And then when I hit the first stage, I was like, okay, how's this going to work? And Joel said, oh, I have a patch. Here you go. And it had just one little bug in it, just a missing end somewhere in one of these 4 statements, which is very easy to do because you have to have a lot of them. And so his code is only looking for the A slice, which is different from i386. So if you have a Spark and you want to boot it from soft-rate, then put your array partition on A. Don't put it anywhere else. This fourth code actually goes, there are subroutines being called here, so this is just a high-level view of it. It essentially figures out if it found a soft-rate volume, it actually parses the metadata in forth and evaluates it and figures out whether we're booting off soft-rate or not. And you can see there's, so in forth, when you pass the function argument, when you call a function, you put the argument first and the name second. And so this actually, the else part here calls the load file function with the name of the second stage bootloader, which the firmware can load from FFS because it understands FFS. And in the soft-rate case, we run some special forth routines that actually do the strategy stuff in forth. It's quite crazy. But I didn't have to do this, and I was very happy about that. So the second stage essentially has to walk the open firmware device tree to find all the disks in the system. This is something we never did before. So before this, you passed in a boot argument from open firmware, and we only looked for that particular disk. And only the kernel would go and traverse the device tree to find disks in the system. And I had to basically port this code from the kernel to the bootloader to ensure that we find all the volumes you have in your Spark. This was quite fun, actually. And but then I had a problem. The problem was that on Spark, we do not have shared memory between the firmware and the kernel. What happens is that you type something at the OK prompt, and this string literally gets passed down to the kernel. So if you type boot-a, the kernel gets boot-a. And the question is then, how do you pass the additional metadata that you discover as you boot, right? And I did some trials like, okay, we can append to this string. So it's a C string right now terminated, so we can just add data. and reallocate and pass a different one. And so I played with passing the UID this way, and it works because this is an ASCII string. However, then I got to passing the mask key from a key disk, and I realized that ASCII won't work. So I tried something like encoding it in hex, which was horrible. And then I looked at what Open Firmware provides, and I saw that you can set properties and the kernel can read them. However, I'm not sure where these are stored, and Katana said, well, there might be an NVRAM, which is persistent, and that means that we would put your mask key into the physical memory of the machine, and somebody stealing your machine would just have to read it there, and so that's also a no-go, right? So I looked around a bit more and then what's happening there, and I noticed that there is one additional argument being passed, which is the entropy seed. So when Theo added entropy seeding to all the bootloaders, he added a ELF segment to the kernel binary, essentially like a new section in the binary, and puts the entropy that was saved from the last reboot in there. So the bootloader reads a file from disk which contains entropy, and it writes it into the kernel binary image before it executes it. And I used the same idea to pass the soft rate information on Spark. And there's actually been talk about getting rid of the boot arc stuff because it's insanely complex, and using this approach in all the architectures. It could be done. There's nothing that would prevent us because we have only F systems at this point. And so here it's we decided to go with a very simple sort of thing that would not really be variable sized and stuff like that. Because all you really need to do to change this format is to roll out upgraded binary that understands both formats in one release, like in the bootloader, and then eventually you can, once you hop 2 or 3 releases, we can phase out the old format because by then you won't need it anymore. So this is how we're going to handle this from now on in Spark, and for soft rate it works pretty well. This is the magic how you do this in C when you're in the kernel and you want to read an ELF segment of your own binary. So I think Matthew gave me this first line that I couldn't have figured out myself at all. And from then on, once you have this, because this is a struct, right? You can just read the section of memory like a struct. And so this is how it's done now. And then we copy the information from this ELF segment in memory to the actual soft rate data structures, and then we clear the ELF section. So yeah, otherwise it's the same as RCA6. From here on, it's the same process, kernel assembles the volumes, and so on. Okay, that was the last slide already. Any questions? Is anybody using key disk boot or something like that? I'm using it on all my systems, on all my laptops. It's great. Okay, not so many yet. I think the instructions were not so clear yet, which is part of why I designed the slide deck, so you can go through it and follow the steps a bit. So if you want to try this, I'll commit the slide deck to the papers page in a while, and you can get it from there and sit down with it and maybe try to get a system up and running like that.
I guess a lot of people are dying to ask, is there a time frame for getting the support into the installer?
No. Not from my side anyway. I'm happy with the way it's not now. It's good enough. The question was, is there a time frame for getting support for this into the installer script? I mean,
The answer is in the next release for a couple of releases now.
yeah, the next release for a couple of releases from now. But the question is really, is that really so necessary? Because I just showed you the commands you need to run, which are like 3 or 4 commands. And if you have some special RAID needs, then you will have to you will want to be able to configure your stuff from the command line anyway, and all the tooling is there. So the installer script basically assumes you have one disk you want to install on, and whether that's a software disk or whatever, it doesn't care. And install boot and so on will handle software disks for you already. So all the glue that was added into these little utilities and the kernel and the bootloaders makes it trivial to actually run a setup like this with a few commands run it before the install script. So I'm not sure if we really need to have a rate configuration scripting stuff that asks you what kind of rate do you want and gives you 100 options like Debian would. So it's for simple ones.
Well, were you in?
Documentation, yeah.
Well, for auto install, yeah.
For auto install, yes. Yes, that's right. I discussed an idea with Uwe that you could add arbitrary commands to auto install. Which is tricky, but that would actually allow you to do this and other things.
The fact that there's no proper way of doing
Yeah,
it.
yeah.
First line in your auto install config is exec.
I don't know, but maybe somebody needs to finish Joel's SR-CTL utility. And I think it really makes sense to have this in a separate program, because doing it in the shell script is not nice. I've tried it. It makes the install a lot bigger, and there's no real need for. I mean, the installer is also not meant to support every setup out there. It's supposed to allow us to do enter installs quickly, and have usable dev setups. And for anything that we need to customize things, you already need to have like custom partitioning and stuff like that. And so it's. Does the auto installer support partitions now? It does?
Yes.
Oh, okay. Thank you. Good. Anything else? Oh, yeah.
Support for crypto on software. You mentioned that people have get it to work, but
The nesting of disciplines. So Joel said that he had a post somewhere on MISC or Tech, which explained the problem. I think it's related to the fact that none of the data structures within the software system actually are designed to support this. And so it works when it works, but we have no idea where it will break down for you. And this is why we don't support it officially, because the system hasn't been designed for this, right?
The other problem is all the soft grade disks attached to the same SCSI bus, and so they share the same number of openings. And so what can happen is you have a certain number of IOs in flight, and they might all be on your first disk, like that'll chew up all 64 IOs, and then when it goes to the next layer and tries to acquire an IO, it doesn't have any, and then it sleeps waiting for the top layer IO to complete, and so then it hangs.
Yeah. So it can deadlock, is what you're saying, right?
And you will or will not see this depending on whether you push enough I/O to eat all the openings at the top layer.
Thank you.
So it's a VW solution. Works when testing, doesn't work in practice.
Yeah, well, it's. Huh? I didn't understand. Yeah, it's. Good. Can I go have coffee? Okay.
Nu pratar jag. Nu pratar jag till er på internet. Ni har missat saker. Okej. Men det kanske är bara stereo innan ljudet börjar sändas och då upptäcker den, nu är det mono, och så sen börjar den.
I luran, jag stoppar i lurarna in här och jag har bara hört till vänster
Ja.
hela tiden, så det är nog vänster. Men vi får kolla, för i stora salen så såg jag att det var båda.
Okej. Men för jag kollade alla streams och på alla streams så var det bara ur en högtalare. Men går det att lösa eller? Går det inte att klicka i OS6 då?
Eller ska vi stänga av helt?
Va? Går det inte att klicka i OS6?